All right, welcome everyone to all the operators and facility engineers tuning in to this explainer. It is great to have you. I'm going to be putting on my 30-year veteran hard hat today to bring you what I consider an absolutely critical masterclass. We're talking about ultra pure water, or UPW systems. And more specifically, we're going to troubleshoot one of the most stressful emergencies you can face in the control room, a mixed bed resin imbalance. When your water purity suddenly tanks and those alarms start blaring, well, you need a structured, reliable response. So today, we're going to walk through exactly how to diagnose and fix this issue step by step.
Here's our quick game plan for today. 1. Mixed bed tech basics. 2. The resistivity drop incident. 3. Hypothesizing causes. 4. Investigating the root cause. 5. Executing the system fix. And finally, 6. Summary and final takeaways.
All right, let's kick things off with part 1, mixed bed technology basics.
Okay, let's dive right into this by establishing why the mixed bed is the absolute beating heart of the ultra-pure water system. Before we even talk about the failure, we gotta know where we sit in the plant layout. So, we take our raw water, right? We push it through pre-filtration to yank out the suspended solids, then we blast it through reverse osmosis to strip out the bulk dissolved ions. But RO isn't perfect, it just isn't. And that is exactly why step 4, the mixed bed, is so crucial. It's the ultimate polisher. After the mixed bed, we hit the water with a little UV treatment, and boom, we have our ultra-pure product.
Now take a look at the internals here of this simultaneous flow service cycle. Inside a mixed bed, strong acid cation resin and strong base anion resin aren't just sitting in separate lazy layers. No, they are intimately mixed together. Why? Well, because as the water passes through, the acid produced by the cation resin is immediately neutralized by the adjacent anion resin. It's like a chemical dance. And this immediate neutralization drastically reduces chemical slip, specifically sodium and silica slip, ensuring we get the absolute highest possible water purity.
So the crucial takeaway here is understanding our normal operating baseline. For that intimate mixing to work flawlessly, the volumetric ratio of cation to anion resin has to be perfectly balanced. Depending on your specific feed water, that expected ratio is usually 1:1 or 1:1.5. When this ratio is perfectly dialed in, your system is going to reliably yield pristine water with a resistivity well above 15 megaohms per centimeter. That right there, that is the gold standard we are always aiming for.
Which brings us to part 2, the resistivity drop incident.
But what happens when that gold standard just completely shatters? Picture this. It's 2 a.m. on the plant floor. You glance up at your SCADA screen, and you see this terrifying number. Product water resistivity has plummeted below 5 megaohms per centimeter. Listen, in the world of ultra-pure water, this isn't just a minor fluctuation. No way. This is a catastrophic loss of purity. Your batch is at risk, your downstream processes are totally compromised, and the clock is ticking fast to find out why.
The chemical fallout of this resistivity drop is what we call slip. When the resin ratio is severely imbalanced, that intimate mixing we just talked about earlier, it completely fails. And this causes dangerous sodium leakage, which aggressively spikes your conductivity and throws off your pH. But even worse, it leads to silica slip. Reactive silica basically bypasses the system completely unremoved. And if this water is feeding a high-pressure boiler or a sensitive semiconductor process, man, that silica is going to cause devastating scaling and critical defects.
Let's move to part 3, hypothesizing the potential causes.
So, the alarm is ringing. We have a severe resin imbalance on our hands. Now we need to hypothesize exactly what physically went wrong inside that vessel. When the ratio is thrown off, it essentially comes down to one thing: missing resin. But where did it go? There are 3 main culprits we always suspect. First, loss during backwash, literally washing your incredibly expensive resin right down the drain. Second, natural uneven wear and tear over time. Or third, simple human error. Maybe an incorrect top-up ratio was used during the last maintenance cycle.
Now, what's really interesting about this slide is looking closely at that second culprit, wear and tear. Notice the cross-linked polymer chains of a typical resin bead here. Over time, under varying flow and pressure conditions, they physically break down. We call this attrition in the biz. The beads literally break into tiny fragments called fines. Industry standard tells us to expect about a 5% attrition loss every single year. So, if one type of resin, let's say the anion, is degrading and washing out faster than the cation, well, your ratio is going to slowly skew until it eventually fails.
All right, part 4, investigating the root cause.
Now that we've got our list of usual suspects, it's time to put on our detective hats and systematically rule out these variables. Think about this for a second. How would you personally isolate the root cause before you actually take the tanks offline, drain out all the water, and crack open those heavy manholes? You definitely don't want to fly blind here. You need hard evidence first.
So here is your veteran investigation checklist. First up, check your raw water analysis. Did the incoming ionic load suddenly spike, exhausting one resin prematurely? Next, go physically look at your backwash overflow. I literally can't tell you how many times over my 30 years I've walked behind a unit and found thousands of dollars of anion resin just sitting there in the drainage trench. Because anion resin is physically lighter than cation resin, excessive backwash flow will just lift it right out of the vessel. Finally, when the bed is fully exhausted and separated, you must physically measure the bed depths with a dipstick. That confirms exactly how much of each resin you actually have left in the tank.
Moving on to part 5, executing the system fix.
Okay, once you've confirmed the imbalance and you know exactly what you're missing, you have to execute this system fix to save the plant's production batch. Here is your strict standard operating procedure. Step 1, run a backwash to completely separate the resins by density and meticulously measure that ratio. Step 2, top up the exact required volume of the missing resin, which, let's be honest, is usually the lighter anion, to hit your target 1:1 or 1:1.5 mark. And step 3, actually make that the most absolutely crucial step. Adjust and lock down your backwash flow rate so you don't just wash all that brand new resin right down the drain again.
But wait, you aren't done yet. Adding the resin is only half the battle. During the final polish step, you must use a dedicated air blower to vigorously and intimately remix that newly balanced bed. After a really good air mix, you rinse downward with feed water until you see that conductivity drop right back to normal levels. And only then is the unit actually safe to put back into service.
Let's bring it home with part 6, summary and final takeaways.
So we've identified the failure, we found the missing resin, and we successfully rebalanced the bed. To wrap up this masterclass, I really want you to remember this quote pulled straight from the plant manuals. It should be the absolute foundation of your operating philosophy. Listen to this. Controlling your hydraulic flow rates is just as important as controlling your chemical regeneration. You can have the perfect acid and alkali concentrations, but if your water velocity is too high during backwash, you are literally throwing your system's media capacity down the drain. I'll leave you with this final, provocative thought. It's so easy to just set it and forget it, right? But mechanical valves drift, pump impellers wear out. So, when was the last time you actually stood on the floor with a stopwatch and verified the backwash flow rates at your facility? Seriously, don't wait for the 2 a.m. resistivity alarm to find out your resin is out of whack. Be proactive, check your ratios, and keep that water pure. Thanks so much for joining me for this explainer today. And hey, stay safe out there on the floor.